So to really understand methane, we really have to look back at when did this happen before? And so to look back, we're going to take a look at the Ice Age, the end of the last Ice Age actually, and compare it to the present day, because there are actually many more parallels than you would think. So here is a graph of the post-glacial sea level rise from the end of the last ice age. And the end of the last ice age really set in the melting did just a little over 14,000 years ago. The first meltwater pulse that happened quite suddenly right here was called Meltwater Pulse 1A, and that raised sea levels looks like what do we have, 40 meters possibly, 30 or 40 meters, that's huge. I mean, think of what would happen if sea level raised 30 or 40 meters today. That would be incredible. But the thing to notice here is that the Meltwater Pulse 1A has a very steep gradient. There were three major pulses that ended the last ice age. This one, and this one. And each one of them, the gradient got a little bit softer, but the first one was very strong indeed. So when this first one happened, the meltwater pulse, what probably started to happen is that, you know, the ice sheets melted as they are today, and that created a lot of cold and fresh water on the top of the ocean where the ice was melting next to. And the stagnant and warm water actually sank because even though it was warm, it was salty, and salty water is very heavy. But it continued to be heated by this geothermal heat that's just indigenous to the Earth system. You know, occurs in varying amounts in various parts of the Earth, and after a while that heat built up and there was a tipping point, and the whole thing just kind of rotated like a lava lamp or something, and it created a lot more melting and really increased the ice sheet melt at that time. So we haven't really gotten to this sort of point yet, I don't think, but we do see a lot of this sort of business going on in Antarctica right now, where we have warm salty water with cold fresh on top. So here's the geothermal heating that we see in Antarctica, and as we can see here on the right, Ross Ice Shelf in West Antarctica, there are areas of geothermal heating that are, some are stronger than others, but in particular there's an area out on the land that's got a lot of geothermal heating, and that's going to be building up under the glaciers and cause additional melt and exacerbation of the ice sheet demise. Now the next thing that we're going to be looking at are some grooves that were created when the last ice age ended. And after the grooves were created, there were a lot of methane pockmarks that became evident. And what we see is that the pockmarks are actually occurring inside of the long grooves. This is a groove from a glacier from the last ice age. It's in the Barents Sea, and you can see here's the scraping. The ice kind of scraped along here pretty deeply. All of this was like glacier scraping along the bottom. But you'll notice there are a lot of little round indentations throughout. These are pockmarks, and they're pockmarks that are left over from methane hydrate that basically thawed and became just methane. And the interesting thing to notice here is that these methane pockmarks are actually inside the grooves. So because of that, we can easily say that the sequence of events when you're going to have a methane emission event, which we are going to have, is that first the ice melts, then the seawater kind of mixes up, and you know, the ice melts some more and it gets even hotter. And then when additional heat comes in and the glaciers are no longer scraping along the bottom, then the methane begins to come up and it creates these pockmarks. This has happened in the past, and it did happen in New Zealand in the past. And there are giant pockmarks greater than a kilometer wide in New Zealand from the historic record. I'm not sure how old these pockmarks are, but they occur and they exist. So the thing of it is New Zealand's got a lot of them, and you can see there are zones of pockmarks and just a massive amount of land that is covered with these methane pockmarks from the past. Here's a blow-up of the methane pockmarks in New Zealand. This is a blow-up at Penn Bay, New Zealand, and some of these pockmarks in here are as big as the Rose Bowl. I mean, it's kind of amazing to think about that you could have an explosion as wide as the Rose Bowl Coliseum in California, but that's exactly what they're saying. So with all of this heat that's coming up right now, the permafrost is starting to melt, and this is really a very scary thing. There's so much permafrost, and the permafrost itself is tied to extremely powerful feedback forces, and we're going to take a look at these right now. So this is the permafrost, such as it exists in nature. You can see that this is Siberia and Russia, and there's a huge amount of continuous permafrost here, just absolutely deep continuous permafrost. It's very, very, very big. As well, we can see it in the northern part of Alaska and the northern part of Canada and in the archipelago. The thing is about permafrost is that it's not really always going to be permafrost. So it's neither perm nor is it frost, because when it melts, it's going to be permamush, and the threat of permafrost thaw is real and imminent and guaranteed. So what we find right now is that the permafrost is just starting to melt, and this process releases both carbon dioxide and methane. The permafrost is in steep decline, and over time it's just going to defrost more and more and more. This graphic to 2100, and as you can see, it's really not going to level out. So one thing about methane and going on a lake, it's a great way to roast marshmallows. But if you don't want to roast marshmallows, you can just know that the generally accepted tipping point for large permafrost store release tends to be in the range of 2 degrees Celsius. As you know, we've gone up 1 degree Celsius already. These lakes within the permafrost where you saw those folks lighting those flares, they're really powerful sources of methane. Methane is also known as CH4, as you can see right here, 1 carbon atom to 4 hydrogen atoms. And it's just like in these lakes, all of this biologic material gets compacted and the methane gets distilled into methane hydrate. But the big problem is that we've already emitted enough carbon dioxide and methane and other greenhouse gases to warm the Earth by between 2 and 4 degrees Celsius long term, and 1.5 to 2 degrees this century. I would personally say that this is very conservative. I expect it's going to be more than that, but that's the most conservative measurement. So here's an example. This is really not so far from home if you're here in the United States or Canada. This is in Canada, and this is a methane eruption in Ontario at a Canadian golf course. A little pond on a Canadian golf course started exploding in methane explosions, and it was at the Indian Hills golf course, and you can see that right down here. Not really so far away from, say, Toronto or Detroit or any of the other Midwestern cities. So this is a real and present danger. This isn't something in the future, and this isn't something far away. So this is the methane monster. No, this is not the methane monster. Sorry, mistake. This is the monster from the Green Lagoon, I think. But the methane monster is this. This is an exploded methane crater in Siberia. These have started to appear all over Siberia, this one in the Yamal Peninsula in the latter half of 2014. This one was discovered, and I've heard there's upwards of 20 of these things now. They're bigger than they look. They're actually 60 meters wide. Well, this particular one is 60 meters wide, and it was nicknamed the Dragon's Mouth because it was an exploding methane crater. And pretty stunning. This, you know, so you can see how big the people are in comparison to the crater. When these things explode, it explodes with a tremendous amount of force. Can you imagine the force that that must have taken? Now, the thing is about this, any level of warming that begins to unlock significant volumes of permafrost's massive store can result in passing a climate change point of no return. I believe that's what we're seeing here as these big methane craters begin to pop up in Siberia. I think we've passed a climate change point of no return, and this is the evidence. So with this, let's turn to the glaciated areas and take a look at some of the great ice sheets of the world. So first we'll take a look at the Columbia Glacier and how it's doing. This is a picture of the Columbia Glacier as it's breaking off at its terminus. So this is the Columbia Glacier as it appeared in 1986, not so very far away from our present. And this is it in 2014. Look how far back it's pulled. This was the terminus before, and now look, it's all the way back here, and it has two terminuses. It's got one here, and it's got one here, and it just continues to pull back and continues to melt and degrade. Another area with great ice sheets is Svalbard. This is the island of Spitsbergen, and it is glaciated at the moment. It is the largest island of Svalbard, but we're finding that, like everything else, is deglaciating very quickly. So let's take a look at Greenland. Greenland is our second biggest ice sheet on Earth, as we know, and it's massive. I think it's like 1.5 miles high, and that would be pure ice. And, you know, it's very big. It's getting very dirty. Look at all this dirt. And the albedo is going down as it collects soot and, you know, airplane exhaust. And all this dirt gets rinsed into meltwater ponds that occur in the summertime. And it gets condensed down and forms a black layer that begins a really extreme melting process at the bottom of these ponds. If Greenland was deglaciated, this is how it would look. The middle is lower than sea level, and it has got mountains around the side of it. Those mountains are kind of holding the glaciers in right now like little pins. But Greenland contains an awful lot of ice, and it really affects our life on Earth. It contains 23 feet estimated of sea level rise if it were to all deglaciate. Here's a picture of Greenland if it were all deglaciated, and you can see the middle has a little lake huge lake in it, and that is because the middle is actually lower than the outsides. It's below sea level. Greenland's melting very quickly. This is how we did over the 2015 melt season in Greenland. We can see we had a really strong start, got to be there above the 2 standard deviations of melt over the 1981 to 2010 average, and we actually went out of the 2 standard deviations in mid-June, but it quickly went back in, and the melt really seemed to slow down a lot in July and August, which is very good. So the thing is about Greenland, though, the ice melt is increasing, and it's contributing to sea level rise sooner and greater than anticipated. This is not good news for us. So interesting to note where it's melting on Greenland. You can see up here, this is really where it's melting right now a lot. It's they've had over 100 cumulative days of melt here in the north. I would have expected it to melt more into the southern regions, but in fact it's melted over on the northern regions more. Perhaps that had something to do with the heat waves we've been having in the Arctic. This is a glacier on its way to the sea and how it looks during the peak months of the summer melt. Now the glaciers are actually increasing in speed. The ice sheets are increasing. All the different little ice rivers, they're increasing in speed, and some of them are going at more than a kilometer a year, more than 1,000 meters a year around the edges. And you can see anything that's orange or kind of a brownish, reddish looking, that is the area that is going the fastest. And the area that is blue would probably be defined as like the continental divide. And in this case, the continental divide is actually ice. So as well, Greenland is getting darker. Jason Box knows a lot about this. He has the Dark Snow Project in Greenland, and he measures albedo. Albedo is how dark something gets. So this is just a comparison in June to see how did we stack up between the average albedo between 2000 and 2009. So taking that average and then taking June 16th to 20th, 2015, what we can see is that the ice is getting a lot darker. That's what this graphic means. And in fact, the place that we're losing the albedo the most is the place where the melting is occurring the most, and that there's a lot of melting going on in the north. So that's why the albedo is it's increasing up here in the north, because the ice is actually getting condensed down and becoming darker as a consequence. Now the thing is about Greenland is there are earthquakes on the ice, but it's not really earthquakes such as we understand them. They're actually icequakes. When these massive ice sheets break off, they're so huge and there's such a force when they break off, they actually cause a measurable earthquake in the 5.x magnitude range. It's really very surprising, but that's in fact what they're seeing as these huge, icebergs calve off. It creates earthquakes as they make their way into the sea. And the Greenland ice sheet melt is picking up speed. And this is a graph that shows you that every year it's picking up a little bit more speed. There are variations, of course, that throw it out of the pattern. 2013 and 14, it did not pick up speed because it pulled back during those years. But look at 2012, look at 2011, 2010. On the melt years, it's picking up speed, and it's picking up speed more. So the thing that's really scary about Greenland and strange things that happen there is, as we mentioned before, there are these large kind of ice melt lakes that occur in the summer, and they have dark bottoms due to all the soot that's condensed at the bottom. They tend to form tunnels that just kind of drill their way down in the ice sheet, and then when they find an exodus, either an internal lake that's inside the ice sheet, or if it finds a way out that puts it out to the sea, then it just flushes this entire lake all at once. And these lakes, which can be quite sizable, can empty in like an hour with the force of water running through Niagara Falls. It's really stunning. So comparing Greenland and Antarctica, Antarctica being our first biggest ice sheet on Earth, Greenland is losing mass faster than Antarctica is at this point. And you can see that depicted here. The incline is much, much stronger. And over time, we expect the exponentiation to really set in. As it is right now, we see Greenland losing more and more ice more quickly on a steeper and steeper gradient. As well, we see the same with Antarctica. but on a less steep gradient.